It's my pleasure to introduce our speaker today, Professor Brian Metzger from Columbia University. Brian did his PhD at Berkeley with Elliott Quadrant and received his PhD in 2009. He then moved on to Princeton University as an Einstein Fellow, where he spent about 3 years, and from there moved to Columbia in 2013. Brian has worked on a wide range of high energy phenomena and time domain astronomy. So things like gamma ray burst, supernovae of various types, novae, various accretion processes, and compact object mergers. And today he's going to tell us the latest results on studies, theoretical studies of neutron star binary mergers and their EM counterparts.
Thank you, Edo. It's a pleasure to be here. So today I'm going to be talking about what I think is a growing, exciting intersection between three fields that's really coming about as LIGO matures towards a gravitational wave observatory. So on the one hand, we have gravitational waves from inspiraling binary neutron stars, which are not the sources they've discovered so far, but they're the sources that they hope to discover next. On the other hand, we have this issue of where some of the heaviest elements in the universe come from. We are increasingly coming to believe that these neutron star mergers, in particular the very neutron-rich material ejected from them, could be a source for producing the heaviest elements through the rapid neutron capture process, the R process. So you have sort of the nuclear physics aspect coming into this, a very old mystery going back to Burbage, Hoyle, and Fowler and Cameron. Where do these elements come from? And then we also have possible direct tests of this by doing electromagnetic follow-up of these gravitational wave sources to try to look for the signatures of these heavy elements being synthesized in the ejecta, something I'll refer to as kilonova emission. And so I think we're really seeing an intersection between gravitational wave physics, nuclear astrophysics, and observational astronomy that's really coming to a head over the next few years. I want to emphasize, I've worked with a wide variety of collaborators, both observational and theoretical. I just want to emphasize some of the contributions, particularly from Daniel Siegel, who's an Einstein Fellow at Columbia, and Rodrigo Fernandez, who's now a professor at the University of Alberta. Okay, so I think most people in this room know that binary neutron stars exist in our galaxy. There's about 10 of them, known as pulsar systems, that have gravitational wave merger times less than a Hubble time. The basic prediction is that they should emit energy and angular momentum and gravitational waves, causing them to in-spiral over time. So if you have a circular orbit of equal mass objects, the period should increase according to this formula in the weak field limit. And in fact, that's what was observed from the Holst-Taylor binary pulsar, essentially confirming that GR works, at least in the weak field regime. And in that particular binary will completely merge in about 300 million years. So these binaries merge. They exist in our galaxy. They merge at a regular pace. It's difficult to estimate how frequently they occur because you have to take the known binary systems and sort of extrapolate for all the systems that we don't observe or don't happen to be in phases we can observe them. But typically you estimate that they merge once every 10 to the 4 to 10 to the 5 years. Okay, so it obviously would take a long time if we had to wait for one of these to occur in our own galaxy, but fortunately once Advanced LIGO reaches its design sensitivity in the next 2 or 3 years, they expect to detect these events out to about 200 megaparsecs, and there are millions of galaxies or more out to that distances. So pessimistically, they hope to detect of order 1 of these events per year, but maybe up to 100 or so. But there are very large error bars in this region, in this rate. Okay. Of course, this wasn't actually the first source that LIGO detected. I'm sure you're all aware that the first source were binary black holes. This is not so surprising because they're much brighter gravitational wave sources, so you can see them much further away. So even a much lower volumetric rate of these events, they would have been discovered first. What was surprising was how massive the black holes were. So this just shows the gravitational waves observed in the Hanford Washington LIGO Observatory and the one at Livingston. You can see the very virtually identical waveforms, which very nicely match what you expect from a merging compact binary, because as they in-spiral, the gravitational waves increase in frequency and amplitude, so you get this sort of chirp-like signal. And then they coalesce, in this case, to a massive black hole, which then sort of radiates down to the stationary Kerr state, and you can even see that spin down. Okay, so this was very, as far as we can tell, consistent with general relativity, and was really the dawn of gravitational wave astronomy, which I'll discuss in a second, that we did actually have electromagnetic follow-up of this event. One of the mysteries that emerged from these first LIGO black holes were the fact that, so there was this one in September, and there was another one last December. They were quite massive compared to the black holes that we know of in our own galaxy and X-ray binary systems. And this is sort of a head-scratcher for many people. How did we get these massive black holes, and how are they able to merge? How are they able to get close enough that they coalesce within the age of the universe? So there are lots of ideas for how this could happen. Avi has a very interesting one. So one thing that we've discussed, which I'll just say offhand, is that maybe these are very massive black holes because they were formed in an extreme environment, such as in the disk of an AGN, where we think massive stars could form. And it's possible that if you do form a black hole binary in an AGN disk, there's a lot of gas and other stars around that could cause it to coalesce quite quickly. So we explored this as a possible mechanism, possible channel for these, although there are many others that are now being actively debated, and we expect to detect more of these over the next few years through LIGO. So obviously one of the things you'd like to do from the astronomy side is try to figure out where these things are coming from, what galaxy are they coming from, where within that galaxy, etc. And to do that, we essentially need to identify an electromagnetic counterpart, because the LIGO interferometers alone only localize the source very roughly on the sky through triangulation. So if you have just the two LIGO interferometers, as we had for the first gravitational wave discovery, the black hole binary was localized to this sort of giant banana-shaped wedge on the sky with a 90% confidence interval of 600 square degrees. And as you probably know, that's enormous compared to the fields of view of most telescopes. But we have been undergoing this revolution in astronomy, wide field telescopes that can cover large fractions of the sky relatively deeply, relatively quickly. And so there was a very nice follow-up effort led by Edo and others, where although the gravitational wave discovery was announced within a few days of the detection, it was followed up after that within a few days by X-ray telescopes, SWIFT, by several optical facilities. I was a part with Edo and others of the dark energy camera, which was the deepest follow-up of this event. There were also several attempts to follow this up in the radio. Needless to say, there was no confident counterpart detected, and that's for maybe two reasons. Even though we were able with some telescope to cover most of this air region, we weren't able to do so with the most sensitive telescopes. So if there was a counterpart, as I'll discuss later, they're going to be quite dim. It's not too surprising we didn't detect it. But more importantly, these are binary black holes. There's not, we think, in general, a lot of matter around them to produce electromagnetic emission. So I'd say prior to this event, there wasn't much of an expectation that there would be a coincident counterpart. Now, things will get better in the next few years. This spring, the Virgo interferometer in Italy is coming online. Within a few years, CAGRA in Japan, and hopefully within a decade, LIGO will move one of its interferometers to India. And so by having these multiple baselines when they detect an event, they'll be able to localize it much better than the 600 square degrees, maybe even tens of square degrees or less for the higher signal-to-noise events. And so it'll be much, we'll be able to, even with these more sensitive telescopes, look very deeply for these counterparts. And so this is just the beginning of what will become a routine exercise, and hopefully we'll be successful with this, especially once we have binary neutron stars. The other thing that this neutron star mergers connect to are the origin of the heaviest elements in the universe. So you probably know that the lightest elements are synthesized in the Big Bang, intermediate mass elements in massive stars, or in the shock waves through supernova. But the heaviest elements, which you cannot form through standard nuclear reactions, thermal reactions in stars, must be formed through some sort of neutron capture process. So that's how you overcome the Coulomb barrier issue, is you have neutrons bombard nuclei and form heavier elements that way. There's roughly half of these neutron capture elements are produced in a site called the R process, just some sort of astrophysical site where you have a very high density of neutrons, so that the rate of neutron capture onto nuclei is much faster than the rate they're able to beta decay. And in this way, you're able to, as I'll show in a minute, synthesize elements which you otherwise couldn't produce. And what all we really know is that there must be some sort of very energetic, explosive event in nature which has a very high density of neutrons. And there really aren't that many contenders for what could be the dominant site producing these. The two people mainly discuss are core collapse supernova or binary neutron star mergers. The supernova models have some problems. Theoretically, they don't seem to work. Neutron star mergers, well, we don't know. There's a lot of uncertainties in the way the neutrino transport is handled in the afterglows or aftermath of supernova, but it seems to not really work. But neutron star mergers do work, so that's a positive. What we do know is that to produce these over the age of our galaxy, you typically need to produce roughly, average of the age of the galaxy, something like 10 to the minus 7 solar masses of elements heavier than 130 per year. So if you had a neutron star merger rate, say, of every 10 to the 5 years, you would need each one to eject about 1/100th of a solar mass. Whereas supernova, you could get by with much less per event. The reason that historically people have favored supernova is that if you look at metal-poor stars in our galaxy, they tend to have abundance patterns of these heavy elements which are actually remarkably similar to those of the solar system, even though the stars forming these were likely polluted by just a few R-process events. Okay, and so it's always sort of thought, well, neutron star mergers, it takes a while for the neutron stars to merge. Shouldn't the galaxy have become much older by then? This is a detailed question that we're still trying to answer. How early in the star formation history of a galaxy can neutron star mergers occur, and then how well can they be mixed to form these metal-poor stars? I should say we now see evidence for R-process pollution in even dwarf galaxies that have been highly polluted by our process, which may suggest that we have a sort of less frequent but more high-yield event like a neutron star merger. But this is something that is one of the motivations for thinking about these binary neutron star mergers. So I'm just going to go through sort of the stages in the merger process. So first neutron star, and then a very closely related thing is when you have a neutron star and a stellar mass black hole. So the two neutron stars in spiral, they eventually merge into a massive object, which is generally too massive to remain a neutron star and will, in most cases, collapse into a black hole. If the equation of state of the neutron star is relatively soft and cannot support a very high mass, or if the mass of this binary is very large, it will immediately collapse into a black hole. What we think happens more frequently is that you go through a phase where you form this sort of peanut-shaped, distorted, hypermassive neutron star, which is temporarily supported from collapsing due to its differential rotation. But then over some period of time, due to, for instance, internal torques, that differential rotation is removed, and then it collapses to a black hole. That could be as short as 100 milliseconds or less, or actually much longer. And typically, because that process requires removing angular momentum from the object, either through internal torques or gravitational waves, you tend to get some matter that has a lot of angular momentum and remains outside of the black hole in an accretion disk. It's even possible that if the equation of state can support a very massive neutron star, or if the initial binary is low mass, that you could actually merge and form an object that is very long-lived or indefinitely stable, even after it's spun down. So it's conceivable that two neutron stars could merge, and the end product could also be a stable neutron star. That's not out of the question, given what we know about how massive neutron stars can be. You end up with a similar process when a neutron star merges with a stellar mass black hole. But here what matters is, again, the mass ratio, more of the binary, more than the total mass. If the black hole is relatively massive, it will just swallow the neutron star whole. If it's a relatively low mass black hole, or it's spinning such that its ISCO radius is relatively small, it will tidally disrupt the neutron star outside of the horizon, and you also end up with an accretion disk around the black hole. So you can get a similar configuration from very different initial systems, and that will be important for the counterparts I'll describe. So I'm going to show you a simulation of two merging neutron stars. This is from Radioactive and collaborators. It's not my work. But you'll see the final stages of the in-spiral. You'll start to get, let's see, try that again. See the final stages of the in-spiral. You'll see pretty strong tidal distortion of the neutron stars, and when they finally merge, you'll see the ejection of material out the outer Lagrange points of the binary. There's also a collision between the neutron stars, which ejects some material dynamically. And this matter is basically completely unbound from the system. And then you have this sort of rotating peanut left over, which is radiating emission through gravitational waves and extracting its angular momentum internally through torques, and then eventually it collapses to a black hole. And as I said earlier, you have this matter that remains outside of the event horizon. Okay, so what type of counterpart might we expect to detect from such an event? It's likely to be a sensitive function of the observing angle with respect to the angular momentum axis of the binary. So the idea has been around for at least 30 years. I believe Ramesh was one of the originators of this idea that accretion of this remnant disk onto the newly formed black hole could power a jet, and internal dissipation within that jet, say shocks or reconnection, could power a short gamma ray burst. And so I'll talk a little bit first about the gamma ray bursts. So again, the idea here is that we generically expect there should be some material in a torus around the newly formed black hole. The properties of these torus are rather novel. They're quite massive and compact. They're very hot, so all of the initial nuclei in the neutron star are broken down into free neutrons and protons. The densities are very high, so the disk tends to be mildly electron degenerate. The photon mean free path is extremely short, so photons are not effective at cooling these disks on any time scale of relevance, but they are hot enough that neutrinos, thermal neutrinos, MeV neutrinos, are produced copiously, and they can, at least for high accretion rates, initially cool the disk to some extent. Weak interactions are actually very fast in the disk, so they tend to come into an equilibrium that sets the composition of the disk, sets the so-called electron fraction. So these disks tend to be very neutron-rich because of these weak interactions, roughly 5 neutrons for every proton or something. So you can do a simple estimate of the accretion time or the viscous time of the torus, given that we expect it will be susceptible to the MRI. There will be turbulence driving mass accretion, and that time scale is, for typical parameters, about a second or a tenth of a second. Okay, and that characteristic time scale and this enormous accretion power are basically the theoretical motivations for associating these with the short duration gamma ray bursts. Okay. I'm not going to say a lot about gamma ray bursts. I think one of the mysteries is exactly how the jets are powered in these events. Most people think that the jets are magnetically powered, possibly extracting the spin energy of the newly formed black hole. To do that, you need a very strong magnetic field. So one of the active questions in this field is how I go from an initial field of 10 to the 12 Gauss or less for the 2 neutron stars, and then we have a complicated merger process with lots of internal rotation, differential rotation, magnetic field amplification, and then voila, at the end, we sometimes somehow have a 10 to the 15 or 10 to the 16 Gauss magnetic field, which is threading the hole, and that's what we need to power the jets we observe, roughly speaking. So Edo has done, I think, and his group have done the best job of sort of making the observational case that short gamma ray bursts come from mergers. And I'm really not doing complete credit to his work here, just sort of half a page here, just describing that evidence. But essentially it comes down to the fact that we can see short gamma ray bursts happening in both young star-forming galaxies as well as old elliptical galaxies. And this is consistent with a range of merger times after star formation, or a range of times it takes the 2 binary neutron stars to inspire, and sometimes if it would take billions of years, the galaxy would have time to become very old. When we look after, unlike the long gamma ray bursts where we almost always see a supernova after them, when we look after the short gamma ray bursts, we see no coincident supernova, even to very faint limiting magnitudes. And also, in some cases, we see offsets of the gamma ray bursts from the disk of their host galaxy, which is consistent with the birth kicks that we expect these systems receive. So I think there's a lot of strong, circumstantial but strong evidence connecting these events. We're still sort of lacking that smoking gun, and that's something that we hope LIGO will be able to provide to us. The challenge is that we think the gamma ray burst emission is beamed into a fairly narrow solid angle on the sky, so only the observers that happen to be within the opening angle of the jet will actually observe a gamma ray burst. And although the gravitational waves are slightly stronger for a face-on viewer than they are in the equator, that still implies that you probably only have a few percent or maybe up to 10% of the gravitational wave events that will have an associated gamma ray burst, even if every merger produces a gamma ray burst. Okay. So that means is that we have to wait for something like 50 LIGO events before the first one will have an associated GRB. Okay, so that's a long time to wait. Certainly, once we make that confirmation, it will be very exciting. It's actually a fairly easy thing to do as long as we have a gamma ray satellite flying, and we should certainly look for coincident GRBs. But we don't expect them from the first one, and so that's motivated a lot of my thought about what are the more isotropic counterparts of these events that we would observe even if the gamma ray burst and its afterglow were beamed away from our line of sight. So that's this idea of a kilonova. So the basic motivation here is that there are several sources of neutron-rich ejecta from the mergers. There's this material ejected dynamically, which I showed you in the movie. It comes out basically immediately by strong tidal forces. This can range between 10 to the minus 3 and 10 to the minus 2 solar masses. In most cases, but not all, it expands extremely rapidly from the neutron star surface. So it retains the very high neutron-rich composition of that interior. So the electron fraction, which is the ratio of protons to total baryons, is typically less than 0.1 for this material. So it's extremely neutron-rich. The other source of mass outflows from these systems, which have received less attention, but I've focused most of my work on, are outflows from this remnant accretion disk that forms. When the accretion disk is initially, when it's very hot, it's a strong source of neutrinos, and these neutrinos can drive mass from its surface in a sort of wind. But more important is as the disk cools and as it viscously expands due to the transport of angular momentum outwards, the free nuclei in the disk recombine into heavier elements, and that releases quite a bit of energy that actually aids ejecting the disk. It also can't really cool at late times because the neutrino cooling is ineffective. So you tend to unbind a lot of the disk in these sort of recombination-powered outflows. And what we find, I'll show you in a second, is that amounts to about 10% of the torus mass. So if your torus is a tenth of a solar mass, you can eject about a hundredth of a solar mass this way. So it can actually be competitive or exceed this, even though this is what receives most of the attention in the literature. But unlike this material, this is ejected over a time scale of seconds, and the electron fraction it may be higher than this material because weak interactions have time to change the composition before the material is unbound. So with Rodrigo Fernandez, we've done a series of simulations of the long-term evolution of these disks. So this just shows you the density, electron fraction, and entropy, and then this is the inner region of the disk. This is zoomed out. The movie isn't super illustrative. I'll show you it, but you'll see the accretion of material. Weak interactions increase the electron fraction, and then you do tend to get these outflows from the outer regions, which are powered by nuclear recombination. But the upshot is that we find that depending on the black hole spin, about 10% of the torus is ejected. It's somewhat slower than the dynamical ejecta. And this seems to be robust. These were 2D axisymmetric hydrodynamical simulations with an alpha viscosity. But we did explore a wide parameter space. And we have to run these for several viscous times, so it's actually computationally quite expensive. We're continuing to improve on this by now doing GRMHD simulations with Daniel Siegel at Columbia. This is just some preliminary work he sent me. But we're now able to run the torus for at least a few hundred milliseconds with the MHD simulations. This is just the density evolution of the disk. And we do see the same sort of qualitative behavior. This is the side view and the top view. And then I'll show you the electron fraction. We have some sort of numerical reconstruction problem in the polar region, so it'll look a bit messy. But you can see that the midplane is fairly neutron-rich, and then the electron fraction rises out of the midplane, and then we're seeing matter. You can't tell it here, but you're seeing matter being blown out of the disk. And it tends to have it still tends to be quite neutron-rich. I'll come back to that in a second. So what we do to figure out so the question is, what is the nucleosynthesis of this material coming out of the accretion disk? Okay, so this is going back to the simulations with Rodrigo, the hydro simulations. So this is our initial torus. The blue points are test particles that are ultimately accreted by the black hole, and the red ones are ones that get unbound in these winds. And then for each particle that gets unbound, we track its thermodynamic history as it gets blown out, so temperature and density evolution. And then for each of those particles, we run them through a nuclear reaction network, which follows the synthesis of these heavy elements. So this is an R-process network, which includes neutron captures, photodissociations, alpha and beta decays, and fission. So if you form very heavy elements, they fission back to lighter elements. And over here, you're seeing the temperature and density of this one fluid element as it decreases, and this will show the chart of the nuclides, neutron number, sorry, this is neutron number, this is proton number, sideways. And then at the top, you'll see a running score of what elements, the abundance of elements versus their mass number. So the generic thing is that as matter expands from NSE, from nuclear statistical equilibrium, you first form these sort of heavy seed nuclei, but there are a lot of neutrons left over because it's very neutron-rich matter. So these seeds will capture neutrons and move this way. Then they'll quickly undergo beta decays and move that way. And it's this process of neutron captures and beta decays that is the essence of the R process, and it moves you up to heavier elements. The valley of stability is over here somewhere. So anyways, I'll finally show you the movie. Oops. Sorry. Not sure why it's not running. Oh, sorry. Okay. So we're capturing neutrons. We shoot all the way up here. Now we're actually already out of neutrons. And then slowly all the elements you've synthesized decay back to stability. And then you can see we end up with this abundance pattern that, at least up there, doesn't look terribly bad compared to the solar system. And over the course of years, I'll show you it one more time. So, okay, so we're synthesizing elements. There's beta decay waiting points I'll come back to in a second, and then everything decays back to stability over the course of seconds, minutes, hours, years, billions of years. Okay, so you end up, so every one of those test particles essentially represents gives you one abundance, and then you add them all together. In this particular, this in the red line is sort of what you get just from these disk outflows. Okay, and so what you see is we get we do reproduce the second and third, and then the black points are the solar system abundances. And you see that we can reproduce sort of the broad features of the R process. Okay, we get the second and third peak, the xenon, the platinum peak. In detail, we have some problems. We're underproducing the rare earth peak here. We underproduce the lighter R process elements. So I want to just, for the students in the audience, I just want to remind you why you end up with these R process peaks. And that's because you have these closed neutron shells at these fixed neutron number of 126 and 82. And near the closed neutron shells, the beta decay times are long. They're stable nuclei. The neutron capture times are short. Are also long. They don't want to capture more neutrons. They're already stable. So this sort of flow of nuclei to heavier energy sort of builds up a lot of density there. And so when you run out of neutrons, that's where a lot of your mass accumulates. And when you decay back to the stable valley, you end up imprinting that nuclear structure on the abundances. And in fact, there's one of the problems with matching to detailed models of, say, the solar system abundances is that many of the properties well off of the stable valley that we're using in our codes, like beta decay timescales, neutron capture cross sections, are not experimentally measured. But many of them will be soon, thanks to this new facility being built at Michigan State. So we will have much better data soon, nuclear data, to try to translate our predictions for the thermodynamics into predictions for the R process abundance. The important point for the kilonova, however, is the fact that this material is radioactive, and so it continues to produce heat after it's synthesized. So this is the radioactive power versus time. If I just had a single decaying nucleus, it would have a constant radioactive heating to the half-life and then an exponential decay. But what happens here is one element decays to another one with a slightly longer half-life, and that decays to another one with a longer half-life. So when you add together the total radioactive heating, it's actually something more like a power law. And on time scales of days to weeks, it's roughly T to the minus 1.2, which is similar to terrestrial nuclear waste, actually. It has a very similar decay to this, it turns out. So the point of the kilonova is that this heating keeps the ejecta hot. If it were just expanding freely, it would become extremely cold. So if it's expanding as a function of time, the density is dropping through this. I'm treating a non-spherical thing as a spherical cow here. But the density is dropping as a function of time, and the time scale for a photon to diffuse out of this ball of gas is dropping as 1 over time, depending on the opacity of the material. So at early times, you may release a lot of radioactive heating, but essentially none of it escapes to the observer because it's all trapped. But then once you reach a time where the expansion time is comparable to the time itself, then that emission can get out. So if you equate those, the expansion time and the diffusion time, you come up with this characteristic peak time scale, so-called Arnett's rule, which tells you the peak time of the emission as a function of the velocity, mass, and the opacity of the material. So for a type 1a supernova, which is roughly a solar mass of material expanding at 10,000 kilometers per second, you predict a transient that peaks at about a week. That's a type 1a supernova with a luminosity set by radioactive nickel decay of 10 to the 43 ergs per second. For a neutron-star merger, where you have about 1/100th of the amount mass expanding even faster, you would predict, if the opacity were the same as a 1a, you would predict something that peaks at about 1 day. And because you produce about 1/100th of the material and the radioactive heating is not too different than in a 1a, you predict something that's about 100 times dimmer. Okay, so this was the basic expectation. We did this calculation in 2010, a more detailed calculation of the light curve, and we predicted something that peaked at about 10 to the 41 ergs per second in optical bands at about a day. And this was actually quite an update on the previous models by Lee and Paczynski, which were about a decade prior, which left the radioactive heating as a free parameter. And so they actually predicted luminosities for these things that could peak between 10 to the 44 and 10 to the 42. So this was really saying, okay, these things are going to be a lot harder to detect than people previously thought. And some people still use these old names like macronova. But what I will say is it actually got worse. So in these models in 2010, we assumed that the opacity was similar to that in a 1A supernova, where it's set by a forest of iron lines, basically form a continuum opacity in the UV and optical. But what Dan Kaysen pointed out is that actually we also synthesized some of these rare earth elements in the ejecta. And these can have a much more complicated atomic structure than that of iron, because they are they have F-shell valence electrons. And so in some sort of combinatorial way, the electron in this atom has many more options, many more transitions. So there are many more lines. And because the opacity is set by this forest of lines, the opacity should be much, much higher. And in fact, it goes as the number of levels squared, so it's actually exponentially larger than if you have iron. So he predicted that the opacity in the optical UV could be 100 or 1,000 times higher than that of a 1A supernova. And so that changes the prediction substantially if it's the case, because whereas before we would predict something that was peaking in the optical at about a day with an effective temperature of, say, 5,500 Kelvin, because the opacity is higher, the ejecta has to expand further and cool further before that radiation can get out. So that pushes the spectral peak into the near infrared. So this, now importantly, if there are some of these lanthanide actinides in the ejecta, that's the important point. So this was sort of the prediction around 2013, and then there was this very exciting GRB, a 130603b. You've probably also heard about, because Edo was very involved with this, where it was a short gamma ray burst at a relatively nearby galaxy, redshift 0.35. It was detected by X-rays, the afterglow of the gamma ray burst. It was decaying in the optical, decaying in the infrared. And then there were some Hubble observations triggered, which got an infrared data point and an optical upper limit at about 1 week after the event. And so if you just extrapolated the afterglow emission, this excess in the infrared was rather substantial. And so you could envision a model where we're seeing the decaying afterglow, but we're seeing a contribution from this rising kilonova emission, which, as I mentioned before, should be predicting and peaking in the near infrared. In order to explain this brightness, you needed about 0.03 or 0.05 solar masses of material. Sorry, the 0.1 should point to that line. So this was very exciting, because if confirmed, it would be the first time we've directly seen a source for producing the R process in the universe. It would confirm the association between neutron star mergers and short gamma ray bursts. But it was just one data point, so we really need to do this with more events to get a sense as to whether this is typical or maybe a sort of outlier. So you can ask the question, can we detect these kilonova following a gravitational wave detection? So here I'm showing, this is basically the I band magnitude of some more recent kilonova models by Jennifer Barnes. If I put a source at the edge of the LIGO volume versus time, and then this is sort of our estimate of the sensitivity to which various telescopes could achieve if they dedicated their night to doing LIGO follow-up. And what you can see is that because these things are peaking in the infrared, even going as far as you can from the ground, they're only peaking at sort of 24th magnitude for a few days. So you can do this with sensitive telescopes like Dark Energy Camera or LSST, but it's going to be very hard to do with some of the smaller telescopes. At least for this sort of fiducial parameter set, a typical hundredth of a solar mass of ejecta. I'll come back later to some ways this might improve. What you'd like to do is to follow these up in the near infrared where these things are much brighter. We of course don't have many wide field telescopes in the near infrared, but we are planning possibly to send one into space with WFIRST. So I'm really hopeful that we can have some capabilities with WFIRST to do LIGO follow-up, because this will be sort of easy for them. I mean, of course they don't have a huge field of view, but by the time WFIRST is flying, hopefully all the LIGO India and all these other things will be around, and we'll have much smaller air regions. So we could detect it possibly even for a few weeks with WFIRST. The point is we want to be able to have a good localization for these. We want to detect them with optical or infrared. All right, so returning though to this question of whether I have a blue or a red kilonova, is it something that peaks on a daytime scale at the optical or in a week in the infrared? It really depends on the composition of the ejecta. So what really matters is whether we have lanthanides in the ejecta. But the only way we can get up to these heavy elements in the nucleosynthesis is if we have enough neutrons. So only very neutron-rich components of the ejecta will produce lanthanides and have this high opacity. More proton-rich or less neutron-rich conditions, we won't actually have enough neutrons to get up here, and we will still have opacities which are sort of similar to those of 1A. So we predict something that's bluer and peaking earlier. And that's why these outflows from the accretion disk are so important, because they could in principle, have a much higher electron fraction than the dynamically ejected material. So you can imagine a picture where if, for instance, the outflows from the accretion disk produced something that was less neutron-rich and did not produce the lanthanides, but the dynamical material, which is primarily coming out in the equatorial plane, did, you could have a picture where you could actually observe both components. So if you're observing it from up here, maybe you see the red emission from the dynamical ejecta, but you also see an early blue component of emission from the accretion disk outflows. And of course, what this will be highly sensitive to, it turns out, is the lifetime of the hypermassive neutron star in the center, because it's a very strong source of neutrinos, particularly electron neutrinos, which can turn neutrons into protons. So generally speaking, the longer the neutron star survives, the more it will irradiate these outflows from the disk, irradiate the disk itself, and the bluer this emission from the kilonova will become. So this is something we tried to quantify by performing similar simulations of the accretion disk evolution, but putting a neutron star in the center as a strong source of neutrinos. And we found, of course, as you'd expect, fairly different evolution. So the rate of neutrino heating above the neutron star is much stronger than if you just have a black hole accretion disk. The electron fraction of the material that gets ejected in the polar regions is much higher if you have a neutron star, because the neutrinos are able to turn neutrons into protons. And so broadly speaking, what we found is that we don't know how long the neutron star will survive after the merger. It depends on some combination of the equation of state and how efficiently angular momentum is being transported throughout that object. So we parameterize it. We just artificially collapse it to a black hole at various points in time: 0 milliseconds, 10 milliseconds, 30 milliseconds, 100 milliseconds, 300 milliseconds, or never. We just let it remain stable. And then we explore the composition of the ejected material as a function of that lifetime. So what we find is if the neutron star is very short-lived, most of the ejecta from the disk is quite neutron-rich, and it will produce exclusively lanthanides. But as the neutron star survives longer, an increasingly large fraction of its ejecta will be above this sort of critical electron fraction and won't produce lanthanides. So the expectation is that, here's the actual abundances. I don't want to say too much about that, but you see this general trend. So essentially the general expectation is that if we have a very quickly forming black hole, the blue emission from the disk will be quite low, whereas its infrared emission will be bright. But the longer it survives, the brighter the blue emission will become, okay? And so if we have a fairly long-lived neutron star in these systems, and it does produce a lot of this blue emission, then this is going to be much easier to detect from the ground, or actually in any way without having to wait for W first, for instance. We could still detect possibly the red component without this emission, but it certainly will help. Okay, and there may also be a viewing angle dependence because if the blue emission from the disk is slower than this equatorial material, then if you're in the equatorial plane, the lanthanides will actually block the disk emission. So it's even possible that you'll have a strong viewing angle dependence of this emission. And so the basic point is that because of this, what we believe to be this very sensitive dependence of opacity on the ejecta composition, we can potentially use these light curves if we detect them as probes of things like the neutron star lifetime or the geometry. So if we measure the redshift of the host galaxy, we know the inclination of the merger, and so we can check it against these types of things. We're not going to have a lot of information from the gravitational waves alone on how long the neutron star survives. We're going to see it in spiral in the LIGO band, and most of the merger itself actually occurs at higher frequencies, and any signals of the hypermassive neutron star, like its quasi-normal modes that we might see in the gravitational waves, tend to happen at high frequencies and are very challenging to detect. So this kilonova emission may be our strongest indicator of how long the neutron star survived. We can even imagine someday taking a spectrum of one of these kilonova. The problem is that at early times when the light curve is peaking, you're seeing the fastest layers of the ejecta. Any lines we might have in the spectrum will be Doppler broadened away. But as time goes on and you peer deeper into the ejecta, especially the slower disk wind, the lines will become narrower, and you can imagine to look for individual absorption features. Now, to do this, we need not only detect these events, but take a spectrum of these. So I think this is a prime science target for future 30-meter telescopes like GMT to try to do this. Okay, or others. Okay, so I want to return just with the last bit of my talk to I think is a very interesting question, which is, does a black hole always form in these systems? Okay, so as I mentioned before, so we know that the maximum mass of a neutron star is at least 2 solar masses. Okay, if the maximum mass turns out to be 2.01, then no neutron stars will do this because they will all collapse to black holes very quickly. But if the maximum mass is 2.4 or 2.5, many of them will possibly produce stable remnants. So if you do produce a stable neutron star from this situation, or even one that just is supported by its solid body rotation and can survive much longer than the hypermassive neutron star, it will likely be characterized by two things. One is it will necessarily be rotating near its breakup velocity because all the angular momentum of the initial binary is, a lot of it's now inside the neutron star. And it will also have a very strong magnetic field. We see this in the simulations where at least the small scale magnetic field is amplified to 10 to the 16 Gauss. Okay. So it's quite conceivable that this is a factory for producing what we refer to as millisecond magnetars. Now we don't necessarily, so my motivation for thinking about these, which actually goes back to before the 2 solar mass neutron star was discovered, and this was really crazy, was that you see evidence for extended emission following short gamma ray bursts. So this is the gamma ray burst itself, and then you see this sort of hump of extended X-rays, a gamma ray burst, and then this sort of second episode of emission. This is old BATSI data, the gamma ray burst, this hump of emission. So this is seen, and it's uncertain, but it's about a fifth of the gamma ray burst detected by SWIFT. You see significant variability in this emission, which strongly suggests that it's coming from the central engine. It's not an afterglow effect from interaction with the ISM. It's actually coming from the engine. So that means that if you believe an accreting black hole is powering the gamma ray burst, it has to be accreting substantial mass for minutes. And you have to understand this weird time profile. Why was it accreting and then off and then on again? And also the energy in these tails can be up to 30 times that of the gamma ray burst itself. So this always smelled to me like there was something long-lived in these systems that was putting a lot of energy out. I don't know if it's a long-lived magnetar, but that's something that we were thinking about. So the basic point is if I have a neutron star with a spin period of 1 millisecond and it has a dipole field of about 10 to the 15 Gauss. By the way, we don't see that in the simulation. We just see a small scale field, but maybe a dipole field will emerge. The spin down power due to dipole radiation is about 10 to the 50 ergs per second. And so the characteristic spin down time, which is the rotational energy in this beast divided by its spin down luminosity, is a few minutes. Okay. So you have the ejecta from the merger, which is expanding, and then in the center you don't have a black hole, but you have a spinning neutron star. It's wind, even though the wind could be fairly spherical, much like in other pulsar wind nebula, it can be redirected into the polar regions. It's confined by the ejecta, so it sort of goes out the direction of least resistance. And so you can get a sort of a transient secondary jet from the system. We don't know exactly how stable this is. It's something that people are continuing to study. But if this jet were to produce additional emission, we showed that, okay, it could kind of produce something that looks like these extended humps we observe. So this is by no means the only explanation for this extended emission, but I think it's certainly suggestive that there could be long-lived magnetars in these systems. And in fact, they could actually boost the emission of this kilonova because they provide an additional source beyond radioactivity. So you have the merger. If you form a magnetar inside the ejecta of the explosion, the X-rays that it produces can thermalize on that material and can contribute to either directly seeing the X-rays itself or producing enhanced optical emission, possibly up to the superluminous level. Okay, so if we see really bright optical or X-ray emission from these, it would possibly be this sort of picture. If you work on superluminous supernova, this is kind of a scaled down version to a binary neutron star merger. Okay, we have been doing searches on short gamma ray bursts to see if there's any evidence for such long-lived magnetars with late time radio observations. And essential motivation is that if you rotate a neutron star as fast as you can, it has a rotational energy of about 10 to the 53 ergs. And assuming this is not lost to gravitational waves, if it actually is lost to magnetic spin down, eventually that energy has to be transferred to the surrounding interstellar medium. So you should create some equivalent of like a super powerful supernova remnant, okay? A very radio bright sort of supernova remnant on steroids or something. But this won't initially be apparent after the event because it has to sweep up its own mass in the interstellar medium. It will brighten over time. So if you do a simple model of how bright that emission should be in the radio emission, it will sort of rise, and then you have a set-off phase. So qualitatively, it sort of looks like this. And so what we did with Wenfei Fong was to follow up several gamma ray bursts several years or decades after the explosion to see if they're bright radio sources. And after following up about 10 of these, we just have non-detections. So unfortunately, the radio emission from this is sensitive not just to the energy input of the magnetar, but also the density of the ISM, which we don't know very well. It could be quite low in these systems. So we're sort of on the edge of placing pretty stringent constraints. So I would say if we believe that the typical density is about 100th of a cc, then we're ruling out these stable remnants in most of these short gamma ray bursts. But we should continue to do these observations in case we can provide, because if we detected one, it would be very compelling. Okay, so I just want to sort of start to finish up by sort of covered a lot of ground. I just want to give you sort of a timeline of all of the stuff I've discussed. So on the bottom here, you see events versus time leading up to the merger, so seconds before out to years afterwards. On the top, you see sort of what emission is being produced. So we have the in spiral, which is producing this chirp signal as the neutron stars coalesce. People have speculated that there could be some sort of precursor associated with the interaction between the magnetospheres of the neutron star. This could give rise to a fast radio burst or some sort of X-ray transient, a precursor emission. This is rather speculative, but certainly we should be looking, for instance, with LOFAR around the time of the merger. Then they coalesce within a millisecond or so. We have this dynamical ejection of material. After the merger, usually we have an accretion disk around the newly formed black hole. It takes about a second, we think, to accrete onto that object, which could power a jet, possibly explaining short gamma ray bursts. It's conceivable in some cases that we could have a long-lived magnetar, which could continue to produce periodic gravitational waves, possibly producing some sort of extended X-ray emission. Within about a second of the merger, you have the R process itself occurring within the ejected material. And then what emission you get after that from the kilonova as this ejecta becomes transparent depends very sensitively on the composition of this material and how fast it's expanding away. I didn't have time to discuss it. The polar regions where the neutron stars collide could be expanding very rapidly away from the merger. It may expand so rapidly that the neutrons don't have time to be captured into nuclei, so you could actually have a skin of free neutrons on the outer layers, which could power something called the neutron precursor timescale related to the decay timescale of a free neutron. But then that's somewhat speculative. But then I think the more certain thing is we're going to have possibly blue and red kilonova emission, which will depend on the geometry and electron fraction. So if it's fairly neutron-rich material, it will produce a red kilonova. That's sort of the assured thing. If we have some higher YE matter, say in the polar regions, that could produce this blue kilonova emission, which is peaking more like a day. And then whatever we produce from this ejecta should go running into the interstellar medium and should produce radio emission. It may not be as bright if it's not a magnetar, but there should be some sort of slow radio flare. It could last several years or decades and be very hard to detect. But it does motivate following these up also in the radio. What do I hope to learn in the next decade? So I don't know if we'll actually learn these things, but this is sort of what's motivating me. I really would like to know are short gamma ray bursts produced by neutron star mergers or black hole neutron star mergers. So if we just keep Fermi flying, or we fly something like Fermi or Swift, and we keep LIGO, and LIGO reaches its design sensitivity and keeps observing, if they don't see anything in coincident with one another in, say, 3 or 4 years, I think we can rule out the hypothesis that all short GRBs come from, or produce, all mergers produce short GRBs. Hopefully we'll start detecting mergers and be able to look whether there are short GRBs, but that's sort of the most pessimistic scenario. I'd like to also see how all of this depends on the angular structure of the jet, because we'll have, if we can measure the redshift of the burst, say, from the kilonova, we'll be able to say what is the inclination of the binary. And we'll be able to compare some of the gamma ray properties to that inclination. Maybe the gamma ray burst emission is brighter if it's directly face on, or if we're slightly off axis, it's dimmer. I would like to see when does the gamma ray burst arrive relative to the gravitational wave chirp. We expect the chirp to conclude, the neutron stars to merge, and then within, say, a second or less, we see the gamma ray burst. Any deviation from that would be a major discovery. What if we saw the gamma ray burst before the in spiral, or what if we saw it 10 minutes afterwards? This would cause a lot of head scratching. I would like to know if neutron star mergers are the dominant source of the R process in our galaxy and in the universe as a whole. So I'd like to see a few of these kilonova, see what kind of diversity of elements are synthesized. Can we learn something again by knowing the inclination of the binary and what we see in terms of the kilonova? Can we learn something about what nucleosynthesis is produced? And I would like to know what fraction of these mergers leave stable remnants. So, what is this telling us? If all mergers left stable remnants, that would be strongly suggesting that the maximum mass of a neutron star is very high. If none of them do, it's suggesting it's quite low. And to varying degrees, LIGO will be able to measure the total mass of the binary. So by comparing the signatures of stable mergers, very bright radio emission, weird kilonova, to what we infer from LIGO, we should be able to possibly learn something about the maximum mass. We'd like to learn if magnetars are responsible for the X-ray activity after short gamma ray bursts, and all of this, how this all ties into the synthesis of these elements. So I'm basically finished. I just want to note on how much the R process has changed since I was a student. So this was from a textbook, or maybe it was just widely distributed, which shows sort of where various elements were synthesized in the universe in 2007. And what you can see is most of the R process were listed as coming from supernova. And I think this was, by and large, the common wisdom. And again, it was mainly what I said. I think it was a combination of the fact that we do see these in old stars. Supernova happened very promptly after star formation. In fact, there was a review article, I won't cite the authors here, but you can look it up if you want, where they gave neutron star, it was on the R process. Where has the R process gone? Because essentially there were problems reconciling supernova models with galactic chemical evolution. We couldn't get the R process to work in supernova. But essentially, they gave neutron star mergers a footnote in this article. The rest of it was on various models of supernova. So this is the footnote. And now there's this recent new chart of the nuclei put out by Jennifer Johnson, which hasn't yet said that binary neutron star mergers create these heaviest elements, but at least there's merging neutron stars ? So I'd like to think that the excitement of LIGO is brought to this field, and many people thinking about it. Maybe we've swung too far. Maybe we are sort of on the bandwagon and with neutron star mergers and maybe beyond what the evidence provides. But I certainly think that this field has changed and people are really thinking about this a lot more, which I think is very exciting. So I think I'll stop there. Thank you.
All right, time for questions. James.
So I'm curious about this extended X-ray emission from short gamma ray bursts. So you said it's maybe 20 times as much energy is coming out of the extended X-ray emission, and it's 1 in 4, roughly, that show that.
Yeah, so 30 times the fluence, the energy that's measured, yeah.
So, like, in principle, there are many off-axis GRVs for which the extended emission is still visible, right? Because presumably the extended emission is from some corona or something that's much wider angle. So there might be a lot of those sitting around that we haven't actually identified in SWIFT or BATSI. In principle, there's much more fluence from all of that X-ray emission than all the short gamma ray bursts.
Yeah, I don't know. I don't think we really know what the opening angle of the extended emission is, but most of these models, you're right, do predict that it could be a wider viewing angle than the gamma ray burst itself. So in principle, there should be a population of, I guess it would be like X-ray flashes that would be the off-axis analogs of these, and instead of the hallmark signature would be the other long, so this would look like a long gamma ray burst essentially, but it would be in a galaxy which was more consistent with those of the short gamma ray bursts. So we did have with HEDI 2, there were a number of X-ray flashes discovered, and we had host galaxies for some of them. I don't know if there were any that were clearly identified in ellipticals, but since that time we really haven't discovered as many. These would be really soft X-ray flashes, so I don't know if we have enough to really say, but hopefully with new wider field X-ray things being considered, this should be a target science to try to find these things.
Hi, Brian. Yeah.
Oh, hey, John.
You talked about different kind of Ejecta give you different kind of light color for kilonovae.
Right.
Is it true that by looking at the R-process pattern, the thermal peaks, you also need a different kind of Ejecta with different YEs?
Yeah, so right.
Would you summarize which kind of Ejecta give you what kind of HP?
Yeah, sorry. So the lanthanide peak is somewhere between the second and third peak.
High.
So yeah, it's A greater than about 150. So the statement is that the events that are produced, the part of the ejecta producing the third peak is what makes the red kilonova, and the second peak and below would be making this bluer emission. Okay. So observationally, it appears that the heaviest elements, at least above the second peak and onto the third peak, appear to be produced fairly robustly between stars. So they don't seem to vary a lot between the metal poor stars. But if you look at the weaker R process, the second and below, it seems to show more star-to-star variation. So it is like somehow nature is finding a very robust way to make these heaviest ones. And so maybe what we're seeing is a dynamical ejecta if you wanted to attribute everything to neutron star mergers, you would say that maybe the dynamical ejecta is present in all of them, that we have differences in the lifetime of the neutron star, say, that attribute differences to the weaker one. Some live for 100 milliseconds, some live for 10 milliseconds. And maybe that imprints some diversity in the weaker R process.
I was wondering, you said several times about differential rotation of the peanut-shaped hypermassive neutron stars. Where does this differential rotation come from, and what evidence is there that it exists in such an object?
Well, I don't know if we have any evidence since we haven't seen one of these yet. but it comes from it's just because you're starting off with two neutron stars and they're merging together, and so sort of I guess it makes sense that the object maybe it's not entirely obvious, but the object that you form wouldn't necessarily be in a solid body state when you form it. But it's rotating, with a T over W, whatever you want to say, your instability parameter, which is above the threshold to get these sort of very non-axisymmetric distortions. So the statement is it's seen in the simulations that you get this differential rotation, but it's not the minimum energy state, so it should go away. And the question is sort of what removes it? Is it removed by gravitational waves, or is it removed by internal stresses from, say, the magnetic field that you expect to wind up by this differential rotation? So the hydro simulations, of course, which don't have magnetic fields, see that it's only removed by gravitational waves. But MHD could be much faster. So this is something people are actively working on.
So, Brian, the lanthanide, actinide opacities,
Yes.
which are a big part of the story,
Yes.
are those based on experimental data, or where do those opacities
Okay. Yes. So this is so they're not. In most cases, these lines are not experimentally measured. So we can barely measure all the lines of iron, and these have orders of magnitude more. So these are based on basically structure models for the atom. So the sort of n-body quantum mechanic models for the atom that sort of create statistical realizations of these lines. And what matters most is not the specific lines, but their density in wavelength space. And so you could take the same code that you use to calculate these opacities and try to calculate a first principles iron nucleus. It's not the real one, but and you can reproduce the opacity of iron to within a factor of 2. So it's been tested for lower Z nuclei, and then they're extending it to these higher Z ones. The bigger issue is, I think now the groups, the Caisson's group and then Frisch-Feyer's group, I think through different codes, find roughly the same answer for the density of lines. What they disagree with is how to turn that into an effective, into an opacity. Because things like the Sobolev approximation are sort of breaking down because the density of the lines is too strong. So that the sort of forefront of this, I think it's sort of at the factor of 2, but it is entirely based on modeling. But the bigger uncertainty now comes in how we turn that into wavelength dependent opacity. And that's super crucial because our predictions in the optical were sort of on the tail. This thing is peaking in the infrared, and exactly how that opacity is falling off going to the optical. I mean, that's all the light curve we have. So this definitely deserves more work. I haven't worked on that a lot myself.
the national labs should be doing this?
The national labs should be doing this. In fact, I gave a talk on this once, and I usually joke that this is all known by someone working in bombs. And Phil Pinto at the end came up to me and said, "Not in these ionization states." So.
Since you were musing about the decade ahead, you didn't mention the possible role of LISA, the space-based gravitational wave detector. And I would think that would have an interesting niche role to play in alerting you to these systems before they reach the last few milliseconds of coalescence.
Yeah. So definitely having, if it's been discussed in the literature, if you can detect them with LISA and then infer their merger time years or decades after to within 10 seconds, then that would, of course, aid all of this because you could be ready, have all your telescopes pointed there. You wouldn't have to receive these alerts. And that would be very crucial if you were looking for some sort of very prompt counterpart that would happen, say, before, even before, So right now, they disseminate the alerts within, They claim that they can disseminate them within, say, 10 minutes or something after the merger. But if you could actually get an alert even before, then you could look before for some sort of something happening right at the time of the merger. So for that, it would be essential.
Well, you mentioned the possibility of a gamma ray burst occurring before the merger. Yeah.
Yeah. Well, in that case, we would hope to just have a gamma ray satellite looking at that part of the sky, anyways. But yeah, this should all be synthesized with LISA. We just have to get LISA in the air, and then we have to wait another several years. So by then we may have something else too, besides LIGO. Yes.
You didn't talk much about black hole neutron star mergers.
Yeah.
Do you think that they could be in any way more observable than neutron star if there's differences in, say, like where the lanthanides go and things like that?
So we don't know the relative rates of these because both of them are uncertain by orders of magnitude. So I don't think we can confidently say that black hole neutron star mergers are rarer than neutron star mergers. But we do need, to get any ejecta at all, we need the black hole to not be too massive, because otherwise it just swallows the neutron star whole. But if you do disrupt a neutron star, you tend to eject a lot more material than you get from the neutron star merger. So that's sort of like a small fraction of the black hole neutron star mergers produce a lot more of these R process elements. So which sort of wins is something, we don't really know at present. So once LIGO tells us the relative rates, we'll have a much better handle on that. But for instance, there wouldn't be any long-lived magnetar from a black hole neutron star merger. So there could be. Broadly speaking, you'd expect there to be more red emission from those than this bluer emission.
So I was trying to read the footnote quickly that you put up, and it seemed that it was dismissing neutron star mergers not on the grounds of abundance patterns, but just of the overall rate of them, that they're too rare.
Yeah, I don't know.
And what was wrong with that argument?
I thought it was based more on abundance. I mean, so we don't know the rates, so I don't know how they could eliminate them based on rates. So like I said before, right now LIGO is probably ruling out a rate of like once every 1,000 years per galaxy would be my guess. So if each one produces a hundredth of a solar mass, as the simulations show, then that should be more than enough. I don't remember exactly what they said. I thought the main argument against them.
But I only got as far as the third sentence. The problem is that
the main argument against them comes from basically the fact that neutron star mergers, like I said, they're rare, but they eject a lot of our process material per event. So you would expect a certain variation. And so if you look at old stars, you'd expect a certain, variation in their our process to iron abundance that would be maybe higher than if they were something that was more common and produced less per event. But they were using a closed box model for the galaxy to figure out how the R process elements were mixed in the galaxy. And really we need to do that in a cosmological context and have some mixing that we can resolve and believe. And so I'd say it was sort of basing it on a very simplified model for how chemical evolution happens in the galaxy. There have been several attempts to do better on this recently, but they're still fairly unresolved. So I don't think we can draw. I still think it's easy to draw a strong conclusion at this point. But we do have Anna Friebel's doing this nice work on, and others, on the Reticulum 2 galaxy, where they see a few stars that are very highly polluted in our process elements relative to the other ones in the galaxy. So it's as if there was one really massive R process event in that galaxy early in its history. And if you go through the numbers, it seems like it would be close to being what a binary neutron star merger would produce. But then you have this question of how did the binary neutron star stay bound in a dwarf galaxy long enough to merge without getting kicked out? So there's a problem there too. I mean, people have thought about it. There are ways out of this. But so I think there is growing evidence in favor of some sort of infrequent high yield event. Now, whether that's a neutron star merger, or whether it's a rare class of supernova, I don't think we're at the right point to say.
All right, let's wrap this up and thank Brian again.